Hello, Chem people. I have a couple things to go through today. First thing is I wanted to answer Ben's question. I'm going to put that up here. It was from yesterday, and it was about, and I'm not sure if he still has this question, but I figured it'd be easier for me to just kind of go through it here. It was the one number 27. And it said approximately 0.14 grams of nickel 2 hydroxide dissolves per liter. So this is per 1 liter of solution. Then it says calculate the KSP. And so okay, so what they're giving you here, right here, is the solubility, but it's not the molar solubility. You first have to change that to the molar solubility because they're saying like 0.14 grams of NiOH2. So Ni, sorry, I gotta do the math here. Ni is 58.69, and then OH2, so that's 17 times 2, 34. So that's 58.69 plus 34 is 92.69 grams per mole. And then what you're going to do is you're going to convert this to moles. So you're going to go 0.14 grams over 92.69 grams per 1 mole. And 0.14 divided by that gives you 0.00151 moles of NiOH2. Okay, so now this is your molar solubility. That's that X. So then what you're going to do is you're going to go NiOH2 with water gives you Ni plus 2 plus 2OH minus, and remember you have like the box and then minus X. Well, that X is your molar solubility. So you have plus X plus 2X. So X and 2X, this is going to be 0.00151. This is 0.00302. And then your KSP value is going to be Ni plus 2 times OH minus squared. So 0.00151 times 0.00302 squared. I'm just going to leave the numbers in. And this gets us 1.38 times 10 to the negative 8. So hopefully that's right. I mean, that should be. I guess I could look it up, but I'm pretty sure that should be your solubility of nickel hydroxide. So the next thing I wanted to show you that doesn't have that value. Did I do that wrong? 0.14 grams of NiOH2. Oh, it's at 20 degrees. Okay. Because, yeah, I was getting a different number than that. I'm just going to check this on my computer here just to make sure that I'm not crazy. Let's see here. I posted this not too long ago. There we go. And this was number 27. Right, okay. So that's good. All right, so now what we're going to do is I wanted to show you another little piece here. And this next piece is called, it's actually a very important topic that we'll see after the AP quite a bit, but you should know it before the AP. It's actually on before the AP. It's called the common ion effect. So now what you're going to see here is if you take something that's like really, really insoluble, so you take AgCl and you dissolve it in water, it's going to go through the normal KSPs if you put it in water. But if you dissolve this with another ion that is common to this insoluble salt, so let's say I want to dissolve AgCl in water, it's just going to do, regular old, very much a whole lot of AgCl there, and then like a couple, Ag plus ions and Cl minus ions in the solution. Well, if you do this AgCl in AgNO3, which is soluble, that means that you're going to have a pile of AgCl on the bottom and then a bunch of Ag and NO3 ions up here. And you're going to make this is going to dissolve much less than it would in water. And I just want to explain why that is. Like, that's the math that you're going to be doing, is explaining that. So let's do AgCl, and you can see how this works. So let's say if I wanted to dissolve, what is the concentration, molarity of Ag plus when, actually let's make this of Cl minus if AgCl solid is added to a 0.0100 molar solution of NaCl. Okay, so here's the interesting part. Okay, so you note that it's a common ion effect question because that Cl that's already dissolved is going to impact the amount of solubility that this AgCl can actually do. So what you're going to have is you're going to do your same old KSP expression here, KSP formula. So, we got our little box and we say ice, and we got Ag plus and we got Cl minus. But in this case, our initial concentration of Cl is not 0. It's actually going to be 0.0100. And so when you go here, a lot of times they'll also ask you for the molar solubility. It's going to be really low. But then you go minus x plus x plus x. And so you'd end up with an x, a 0.0100 plus x. And then solving for this, your KSP of AgCl is 1.6 times 10 to the negative 10th equals the Ag plus times Cl minus. And now you've got an x and a 0.0100 plus x. So, okay, so now if you can kind of jump ahead with a little bit of math here, you could realize that this x is going to be ridiculously small, like ridiculously small. So, so what you can say is, like, all right, so now I got, I can plug in these values, x and 0.0100 plus x equals 1.6 times 10 to the negative 10th. But this x is going to be so small that 0.0100 plus x is going to be basically 0.0100. But we have our 89, so we'll just solve it with that. But if you, it's not going to be anything different. So, so anyways, F2 solve. and we go x times 0.0100 plus x, close parentheses, equals 1.6 times 10 to the negative 10th, comma, x, close parentheses. Now, I'm going to guess it's going to be 1.6 times 10 to the negative 8th, because if you do that, you're just basically going to divide by 0.0100 for 0.0100, not the plus x here. But let's see what we get, and that's exactly what we get. X equals 1.6 times 10 to the negative 8th. So feel free to do it with the 89, because you got your 45-minute test. You're going to have your calculator because it's all FRQs. But if you get stuck and you don't know what to do, chances are that you could eliminate that plus x. It's going to be really, really small with these numbers. So the math becomes super easy. You can do it in your head. 1.6 times 10 to the negative 10th equals x times 0.010, divide by 0.01, yeah, and then you're going to end up with 1.6 times 10 to the negative 8th. Okay. So now let's do it with a little bit more difficult numbers. So I'm going to do, this is page, where is this one? Page 648. Page 648, and it's example 16.4. So they said, calculate the solubility. Okay, I'm just going to throw in molar solubility. They'll pretty much always put molar solubility, but we could just say solubility of solid CaF2 with a KSP of 4 times 10 to the negative 11 in a 0.025 molar NaF solution. Okay. So, it's really not that bad. Like, you do these questions. They're not bad at all. You take your insoluble salt, you set it up with your, simple reaction here. And you go, here's your setup. And now it's what this one is going to be a 0. This one is going to be a 0.025 because that's your initial concentration of F, not the 2. The 2 is over here for the change, but it's not, that 0.025 is because of that. Then minus x plus 2x. Okay, so now we end up with x, 0.025 plus 2x. And, we solve for our KSP, so our KSP expression is going to be Ca plus 2 F minus squared. You plug in these values, x and 0.025 plus 2x squared. You can kind of see, like, okay, this is going to be, the math, if you wanted to do it without a T89, is going to be a lot harder. It's still, this 2x is still going to be really small, but let's use our 89 because we got it, and solve for this question. So x times 0.025 plus 2x squared equals 4 times 10 to the negative 11th, comma x. Okay, so now if I was guessing, it'd be kind of hard because you got 0.025 squared is gonna what is that, 0.00625, I think. Yeah, I don't know what that is. It's gonna be, it's still not, the x is still gonna be ridiculously tiny. And so we get 6.4 times 10 to the negative 8th. And that's with your 89. If you were just doing this and just eliminated that 2x, we'll probably end up getting the same exact number. So 4 times 10 to the negative 11th divided by 0.025 squared, and you get the exact same number. So this, okay, so in these things, if you get a common ion question and it's a multiple choice, you're probably gonna want to eliminate that 2x to make it super, super easy for you. But since you have your 89, just throw it into the 89 and do it, because, you know, even though the values are the exact same thing. Okay, I did want to show you one more thing, and this is something that you guys already know. So it's going back to the Q versus K. So you'll get a few questions on this, and then I'll show you a Q versus K question. So in these ones, you know, Q is always like your initial conditions. And so the question that you'll probably get will be, will it precipitate? That's the question, because if Q is less than K, that means you don't have enough product. And if you think about what precipitates, you know, like what we're doing with these things, that means you don't have a large enough value to go backwards. So your precipitation means the reaction has to go back to the solid. And if you don't have a high enough initial conditions, you're not going to get any precipitate. Like, it can't go back. You're not going to go back to the solid. So for instance, like, you know, AgCl, Ag plus, and Cl minus, like, you just don't have enough value to go back that way. It's just not going to do it. So, so let me show you a question. These are actually fairly easy. Solution is prepared by adding, so this is, I should tell you what the page is here. This is 650, 16.5 is the question. And it says, a solution is prepared by adding 750 milliliters of 4 times 10 to the negative 3 molar CeNO33 to 300 milliliters of 2 times 10 to the negative 2nd molar KiO3. Will CeIO3 precipitate? Okay, so now you get a question like this. You know you're looking for Q and K. So the only trick you have to do is to find your concentrations of Ce and IO3. So with the KSP expression, remember, you go CeIO3, 3, water, and then plus 3, AQ plus 3IO3 minus AQ. But now they're giving us concentrations at the beginning of Ce and IO3. So what we have to do is solve for our concentrations of our initial Ce plus 3 and our initial IO3. And hopefully, if you were paying attention, you saw the volumes of these things don't add up to 1 liter. They're actually 1.05. It's like these together are going to be 1050 milliliters. So that's 1.05 liters for both of them. Now you just have to find the moles of IO3 and the moles of Ce. And we know how to do that. So our CeNO3 I'll do up here. Hopefully you guys can see this. Yeah, okay. CeNO3, molarity equals moles over liters. And so we got 4 times 10 to the negative third equals X over 0.750 liters. 4 times 0.75. And that gives me 0.003 moles of CeNO3. That's from here, 0.003 moles. And then I got to do my moles of IO3, so I'll just do that over here. The KiO3 is 2 times 10 to the negative 2 equals X over 0.3000 liters. X equals 0.00600 moles. So now that's 0.00600 moles. And let's solve for those values. 0.003 divided by 1.05 gives me 0.00286. And this one is 0.006 divided by 1.05. And that gives me 0.00571. Okay. And now what you're going to do is you're going to plug these into your Q. So my KSP of this one up here, my KSP of this is going to be CE plus 3 AQ. I don't need the AQ here. CE plus 3 times IO3 minus cubed. And if we're solving for Q, we're going to just plug those numbers in. 0.00286, 0.00571 cubed. Okay. Oh, oops. Times 0.00286. And that gives me 5.33 times 10 to the negative 10th. Okay. So, my KSP of CeIO3, did I just erase it? Oh, I didn't write it in. Okay. The KSP is 1.9 times 10 to the negative 10th. And so then if we were talking about our Q versus our KSP, Q is a tad larger, so we would say Q is greater than KSP, and the answer is yes. Precipitate will occur. Precipitation will occur. Because Q is, okay, so you got more products than you would have at equilibrium. So the reaction would have to go backwards. And we'll calculate that mañana. So that was a long lesson there, but a lot of good stuff. So I'll give you a couple homework questions on this. All right. Speak soon.